Potential energy of an electric dipole in an external electric field. I have already posted a video on potential energy of a single charge as well as multiple charges in an external electric field. If you have not yet watched that video, click the I button in order to watch that. We considered only positive charges in the previous cases. In this video, we are discussing a dipole in an external electric field. That means a positive and negative equal charges separated by a small distance in an external electric field. But before we start this topic, please watch the video completely so that you get all points cleared. It is a derivation. And if you think the video is useful, do like the video, share the video with your friends who may also be benefited, and also leave your valuable feedbacks as comments in the comment box below. If you have not yet subscribed my channel, subscribe it now and press the bell button and all button for notification of more videos like this. As usual, subscriptions are totally free. My name is Ananthavalli. I welcome you all to this new video from my channel. Thank you very much. Come, let us start the class. For calculating the potential energy of a single charge or multiple charges in an external electric field, what did we do? We brought the charge or charges one by one from infinity to a known location in the electric field where the electric field magnitude is given. The magnitude of the work done to bring the charge from infinity to that location is calculated, and that is equal to the potential energy of the charge in that location. But here, since it is a dipole, we have to consider the positive and negative charges together, which are kept at a distance. This is the electric field. The arrowhead shows the direction of the electric field. Electric field is a vector quantity. The field lines are shown evenly spaced, so we assume that it is uniform electric field. Two equal but opposite charges, positive Q and negative Q, separated by a distance 2a, is placed in the electric field. The most important property of the electric dipole, as you know, is its dipole moment P. Dipole moment P is directed from negative charge to positive charge. It is a vector quantity. Direction of dipole moment and direction of electric field are at an angle theta. You have already learned that when an electric dipole rests at an angle to the electric field, then a torque is developed. What is torque? Torque is nothing but turning force. As a result, the electric dipole rotates and aligns itself parallel to the electric field. In this case, it rotates in the clockwise direction. That is, the positive charge moves downward and the negative charge moves upward. Now, the dipole moment and electric field are in the same direction. That is, theta, the angle between these two vectors, becomes 0. Then there is no torque. Dipole is then in stable equilibrium. We will consider this angle theta as theta 1. What is the expression for calculating torque? Torque is equal to PE, that is dipole moment multiplied by electric field. One vector multiplied by another vector gives a third vector. Torque is a vector, so we have to use cross product. So it is equal to PE sin theta. Theta is the angle between P and E. Under the influence of this torque, the dipole undergoes a displacement, angular displacement of theta 1. The angle between the two vectors and the angular displacement of the electric dipole is the same. The work done, W, in rotating the electric dipole by an angle theta 1 can be written as PE sin theta multiplied by theta 1. PE sin theta is the force and theta 1 is the angular displacement. Work done is equal to F into S. So S is the angular displacement theta 1. W is the total work done. Torque, as I said earlier, is PE sin theta. P and E are constant, but this theta goes on changing. Therefore, torque is always changing. Therefore, work has to be calculated by integrating the delta W or the small work done for each little bit of angle through which it is turned. We need to really find out the potential energy of the dipole kept in the external electric field. So, an external torque almost equal to the existing torque is supplied to the dipole so that the existing torque is cancelled. An external torque is applied in the anti-clockwise direction. The electric dipole rotates in the anti-clockwise direction by, say, an angle equal to theta 2. So the dipole is turned from theta 1 to theta 2. How can we determine the work done in turning the dipole from theta 1 to theta 2? Dipole moment and electric field remains constant, but torque keeps on changing as the dipole moves from theta 1 to theta 2 through small angles. So, dW, that is the small work done for each d theta, should be calculated and then integrated as we said earlier. dW will be equal to PE sin theta d theta. Total work done W will be equal to integration of dW from theta 1 to theta 2 equal to integrating P sin theta d theta from theta 1 to theta 2. P and E are constants, so we can take it out. So PE integrating from theta 1 to theta 2 sin theta d theta. Integration of sin theta is equal to negative cos theta and integration of d theta is equal to theta, which is nothing but theta 2 minus theta 1. So this can be written as negative PE cos theta from theta 1 to theta 2. This will be negative PE cos theta 2 minus cos theta 1. This is the work done in turning the dipole from theta 1 to theta 2. The external work done in turning the dipole from theta 1 to theta 2 is stored as potential energy in the dipole. That is, potential energy of the dipole in the external electric field will be equal to the difference between the external work done in turning the dipole through theta 2 and the work done by the electric field to turn the electric dipole through theta 1. And that is the change in potential energy, which can be represented as delta U. Delta U means final potential energy U2 minus initial potential energy U1. So, if you are asked to derive an expression for change in potential energy, that is the energy stored in an electric dipole kept in an external electric field, you have to write up to W is equal to negative PE cos theta 2 minus cos theta 1. You have to draw the diagram and derive this equation. I hope you can easily make out the work done in turning the dipole through theta 2, that is final potential energy, and also the initial potential energy from this equation. If you find it difficult, I shall help you. In the above equation, substitute for W. Then the equation becomes delta U is equal to negative PE cos theta 2 minus negative PE cos theta 1. From this, you can easily understand negative PE cos theta 2 corresponds to U2 and negative PE cos theta 1 corresponds to U1. So, you can also give the expression for final energy and initial energy of the electric dipole in the external electric field. Such questions are also important for the examination. If I could clear your doubts, please support me by subscribing my channel and also like my video. Share the video with your friends and also leave your feedbacks as comments in the comment box below. Press the bell button and all button for notification of more videos like this. Thank you very much. We will meet in the next video with another important topic like this. Till then, bye. Take care.